Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the new webinar series with academics of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarghiti from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open today our third webinar of the season with Professor Tommaso Melodia from Northeastern University from USA. Please submit your question via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, please stay online. I will moderate the Wisdom Corner, live life lessons. So Professor Melodia agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. So I'm very pleased now to introduce Professor Akilditz, Editor-in-Chief of the ITU Journal on Future and Evolving Technologies and President of TRUVA. So Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Tech University. And Professor Akilditz has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals and highly cited at the top of the most prestigious international rankings. Ian is also visiting distinguished professor in several universities around the world. And his current interest research are in 6G, wireless systems, terahertz communication, metaverse, and communication in challenged environments. So Ian, thank you. The floor is yours to present our speaker and to moderate the Q&A session.
Thank you, Alessia. Distinguished guests, esteemed colleagues, and honored participants, good morning, good afternoon, and good evening, wherever you are joining us from across the globe. A warm welcome from Atlanta to our international audience. It is both a privilege and pleasure to inaugurate Season 4, Episode 3 of the ITU Journal on Future and Evolving Technologies, in short form ITU-JFET, webinar series. This season continues to raise the bar with an exceptional roster of thought leaders, and today we are honored to introduce one of the most distinguished minds in our field, Professor Tommaso Melodia. Before we proceed, allow me to take a moment to reflect on the vision and transformative impact of our journal. Launched in December 2020, our journal was conceived with bold mission to bridge academia and industry, accelerate innovation, and foster global collaboration at the frontiers of research. As an open access journal, we are committed to democratizing knowledge, ensuring that groundbreaking research is accessible to all, free of charge for both readers and authors. Every submission undergoes a rigorous peer review process, upholding the highest standards of academic excellence while emphasizing real-world applicability and timely innovation. The journal's success is a testament to the dedication of an extraordinary team. I extend my deepest gratitude to Sijo Ono-san, Bilal Jamusi, Alessia Magliarditi, Erika Campilongo, Maria Otero, and the other Maria, and countless others whose relentless efforts have shaped our journal into the premier platform it is today. We invite you, researchers, innovators, and industry leaders, to contribute your papers to our journal. If you have ideas for special issues on emerging technologies, we welcome your proposals. It is now my great honor to introduce today's webinar speaker, a trailblazer in wireless communications, Internet of Things, and network systems, Professor Tommaso Melodia. Tommaso is the William Lincoln Smith Chair Professor in the Department of Electrical and Computer Engineering at Northeastern University in Boston. As the founding director of the Institute for the Wireless Internet of Things and the director of research for the NSF Power Project, which stands for Platform for Advanced Wireless Networks Research Project Office, he leads cutting-edge and transformative research in next-generation wireless and network systems. Dr. Melodia earned his laurea degree summa cum laude in integrated BS and master's degrees from the University of Roma, La Sapienza, and his PhD in electrical and computer engineering from the Georgia Institute of Technology in 2007. An IEEE Fellow and NSF Career Award recipient, Tommaso has been recognized for his pioneering contributions for wireless systems and Internet of Things. His distinguished honors include the 2017 College of Engineering Faculty Fellowship and the 2018 Søren Boos Outstanding Research Award, the highest research accolade in Northeastern's College of Engineering. Tommaso is a trailblazer in wireless networks, Internet of Things, and cyber physical systems, while a prolific record of groundbreaking research. His influential and pioneering publications have earned 27,000 citations and an H-index of 66 according to Google Scholar, underscoring his significant scholarly impact. His work has been consistently supported by leading agencies, including NSF, DARPA, Office of Naval Research, Air Force Research Institute, and Air Force Army Research Lab, demonstrating its critical relevance to both academic advancement and national defense innovation. Tommaso has held prestigious editorial roles for leading journals, including IEEE Transaction Wireless Communications and IEEE Transaction Mobile Computing and Elsevier Computer Networks. A recognized leader in his field, he has chaired flagship conferences such as InfoComm 2018 as a program chair, IEEE SECON 2019 as general chair, and ACM Nanocom 2019 and ACM WoVNet, which is Underwater Wireless Communication Conference 2014, shaping cutting-edge research discourse. Currently, Professor Melodia serves as Director of Research for the Platform for Advanced Wireless Research, as I mentioned before, Project Office, at a groundbreaking 100 million public-private partnership establishing 4 city-scale wireless research platforms to propel the future of U.S. wireless innovation. Co-led by Northeastern University and U.S. Ignite, the Power Project Office oversees the program's strategic deployment, operations, and transformative impact on next generation wireless systems. On a personal note, I first had the privilege, actually, we have a long story in the background, but I'm cutting it short. I first had met Tommaso in November 2002. It was 23 years ago, IEEE Globecom in Taipei in Taiwan, where his exceptional intellect and relentless drive left an immediate and lasting impression on me. Not long after, he joined my research lab at Georgia Tech, where he embarked on his PhD journey. Together, we pioneered groundbreaking work in wireless multimedia sensor networks and underwater wireless communication networks, producing seminal results that helped shape these emerging fields. His contributions were not only innovative, but also instrumental in advancing our research into new heights. His brilliance, discipline, and relentless work ethic were unmistakable. Following his PhD graduation in 2007, Tommaso's career has been nothing short of extraordinary, a remarkable trajectory defined by groundbreaking research, visionary leadership, and widespread acclaim. His work has not only pushed the boundaries of innovation, but also has earned him well-deserved recognition as a leader in this field. I take immense pride in his journey from a promising researcher to a global authority in wireless systems. His achievements are a testament to vision, perseverance, and excellence. Thank you, Tommaso, for joining us today. We eagerly anticipate an enlightening and inspiring presentation from you. Without further ado, please join me to welcoming Professor Tommaso Melodia.
Well, good morning, afternoon, and good evening, everyone. Thank you, Professor Akildis, for this great introduction. It's been a fantastic journey in the past 20 years. I'm very grateful for the mentorship that I received from your, you're convincing me to come to the United States to work with your lab, and I think that's that has put my career on a pathway that would absolutely not have been possible otherwise. I'm very grateful for all the fantastic work that we did while at Georgia Tech. That's been really an exciting journey and something that has set us on an incredible path of innovation. So I'm going to try now to live up to the fantastic introduction that I have received, and I'm going to start by sharing my slides. Can you see the slides in full screen mode?
No.
Okay.
Yes,
I'll
that's
assume
perfect.
that.
Thank you.
Oh, you can?
Okay. Great. Thank you. All right. So today I'm going to talk about work that we've been doing in what we call Open6G. Open6G, and we're going to be looking at a number of different topics related to our work on Open6G, our orchestration, conflict management, and explainability for the next generation of wireless systems that are going to be AI-powered. So I wanted to start by acknowledging our sponsors, first and foremost, the OUSD Future G program that has been seeding and funding this effort, the NTIA to the Public Wireless Supply Chain Innovation Fund, a fund on the Chips and Science Act that is supporting Open RAN research, the National Science Foundation that has been consistently funding our research, and especially also a lot of our testbed and experimental capabilities, and the Oran Alliance and Industry Alliance for Open Radio Access Network that has been also funding some of our experimental work. All right, and I also wanted to acknowledge key members of our labs and institute. Without their contributions, this work would never have been possible. There's a lot of people that have contributed to this work. I wanted to acknowledge specifically Salvatore Doro, Michele Polese, Pedram Johari, and Leonardo Bonatti. Without their work and leadership, we would not be where we are today. Okay, so what are we trying to do with Open6G? We're trying in many ways to rethink the cellular architecture, right? Today's cellular networks are based on the notion of monolithic base stations. What are monolithic base stations? They're base stations where hardware and software are all intertwined together. They're part of the same system, and it's extremely hard to update, improve, and reconfigure the functionalities. This leads to vendor lock-in, meaning that a cellular network of a specific cellular operator needs to be based in a certain area on hardware that all comes from the same manufacturer, and very limited competition and somewhat of a lack of innovation. Right? Today, if you want to build base stations for the cellular industry, you need to be able to build complete products, right? And have expertise in-house that goes from antennas to analog front ends to the baseband processing, protocols, hardware, software, all together. It's a very complex process that requires, to have companies with significant amount of engineers, and it's very hard, if not impossible, for smaller innovative companies to compete and innovate in this space. Current base stations and cellular networks are also very hard to observe and control at scale. They're closed boxes. We cannot see the status of the system at different levels of the protocol stack. We also cannot reconfigure the network at scale. And this leads to a big gap between what we know about theory, right? We know a lot. There's been a lot of theory that's been developed over the past 20 years on cellular networks in core academic conferences like Infocom, Mobicom, Mobihawk. But all of this theory cannot be applied to real system, right? There's a lot of manual configuration. If you need to configure a network, you need to send a lot of engineers on the ground to manually configure the network. There is a big gap with what you can do in practice. It's also very hard to introduce new services for operators that can be monetized, right? If the hardware infrastructure doesn't support that from the get-go. So you have networks with single vendors and low resiliency. You have complex and expensive update cycles because you need to improve the hardware, and you do that every 10 years. We have 4 of 5G and beyond, right? Was that we were going to be able to support diverse and heterogeneous use cases, ultra low latency, enhanced mobile broadband, cyber physical systems, and IoT. And when we talk about 6G, right, the initial documents that are laying the vision for 6G are talking about even more exciting applications like integrated sensing and communications, integrated AI and communications, ubiquitous connectivity and integration between terrestrial network and non-terrestrial networks. But all of these exciting applications require flexible and programmable network architectures, very far from what we see on the ground today. Right? Also, networks in 5G and beyond, certainly in 6G, are becoming increasingly complex. You have a diversity of devices, right? Not only cell phones and smartphones, but a lot of different IoT devices with different processing and capabilities and needs. You have a diversity of spectrum. 5G introduced millimeter wave. It hasn't been a great commercial success, but likely this is going to be part also of 6G. 6G is also going to be introducing the so-called FR3 band between 6 and 24 gigahertz. There is a lot of interest today for this spectrum. And there's a lot of discussion also on using terahertz, especially for backhauls, sub-terahertz links for 6G. There's also a diversity of protocol stacks, certainly coexistence between wireless protocol stacks and wired protocol stacks. But in 6G, there's also a lot of interest in integrating non-terrestrial networks, potentially underwater networks. And so that will only increase the complexity and the diversity of the system that needs to be managed. And to manage all of this complexity, we need network architectures that are going to be able to support automation, so automated configuration. We can't think of configuring the millions of parameters that are going to be part of these very complex systems in a manual way. We're going to need intelligence and automation techniques to automatically morph the network into a system that is able to provide the service that we need to offer in an optimal way. I talked about spectrum. This is just reiterating the point. FR1 and FR2 were part of 5G. FR3 and FR terahertz are going to be potentially part of 6G. This is very likely to happen, especially for FR3. And so we need also architectures that are able to flexibly and automatically manage the spectrum in a way that it's different from what we've been doing in previous generations of wireless. Okay, so in the world of cellular networks, there hasn't been, until recent years, a lot of evolution in terms of developing programmable software-first architectures. in the world of wired network, wired and enterprise networks, there's been at this point for 10, 15 years, the concept of software-defined networking, right? Software-defined networking, which builds on ideas that have been developed in the research world in previous years, but it has primarily two core ideas, right? One is separating the control plane from the user plane, which is something that in the 3GPP world, it was already known, but this also now came to the internet and to the Ethernet world. And also the idea of introducing the so-called SDN controller. The SDN controller is basically an abstraction through which one can inject control programs that control the routing functionality from a programmatic and centralized abstraction, changing, departing from the traditional distributed abstraction of internet routing that had been at the core of the development of the internet. Another core idea that comes from the world of wired networks is the notion of network function virtualization, right? Network function virtualization says basically, well, let's separate clearly hardware from software and implement networking functionalities in a virtualized fashion in software and let them run on white box hardware, okay? For example, the core of 5G networks has already been designed with network function virtualization concepts. But these notions have not made it to the run. So the idea is you have virtual network function, a bunch of different virtual network functions that run on your favorite virtualization technology. It can be virtual machine, can be containers, etc., on a virtualization layer on physical hardware. And then you have network orchestrators that are in charge of doing two things, basically, right? Managing the resources, the physical resources that provide the virtualization infrastructure, and also managing the virtual network functions, the life cycle, instantiating the containers, replacing the containers if they're not functional, etc. Okay? So with this notion, now this notion of softwareization and network virtualization, in the last couple of years, have been making it into the architecture of the radio access network. And in particular, the ORAN Alliance, which is an industry alliance that was originally spearheaded by operators, has been leading this movement in the direction of open, programmable, and virtualized wireless systems, right? So the idea is you have your traditional black box base station, right? The piece of hardware that is sitting on a tower. It's a little more complicated than this, of course, but just to get a sense, right? With all of the different functionalities at different layers of the protocol stack that are embedded in the hardware, right? Now, all of these functionalities are moving to a set of disaggregated entities, right? That are interconnected with one another with a set of standardized interfaces, okay? So we have the radio unit, or the RU, which is basically a software-defined radio. It's the only real piece of wireless hardware, right? And that's gonna be close to the antenna in a cell site, proprietary cell site. Then you have an open fronthaul interface, which is usually an optical interface, where you're gonna have a distributed unit that communicates with the radio unit. The distributed unit can be virtualized in edge cloud, right? And it basically runs all the baseband processing functionalities and some of the medium access control and the link control functionalities. Then you have another standardized interface called the F1 interface, through which the distributed unit is connected to the centralized unit. Centralized unit is in charge of the higher layer functionalities like radio resource control, right? And other layer 2 functionalities. Again, virtualized. It can be one centralized unit controlling multiple distributed units, right? And now you have disaggregated the base station into different components, the radio units, distributed unit, and centralized unit. You can have different vendors come in and tackle only one of these different components, right? You don't have to have all the expertise in-house for all of the different parts. They're connected with a clear, well-defined, well-divided architecture. And it's all virtualized in software, of course, apart from the radio unit. This is one of the innovations of the Open RAN architecture. The second innovation is the introduction of the so-called RIC, or run intelligent controller. What's the run intelligent controller? It's an abstraction, right? Similar conceptually to the SDN controller that allows you to observe the status of the protocol stack of this disaggregated, distributed radio access network, right? You can see all of the parameters in the near real-time RIC. And then you can run control applications that are known as xApps or rApps. We're going to talk about this. These are control applications that observe the status of the network, react to the status of the network, and impose configurations of the network on different time scales, morphing the behavior of the network into a specific configuration to provide optimized service to certain users. Okay. Now, in Open6G, it is our project at Northeastern, we are looking at open, programmable, virtualized, and intelligent beyond 5G networks in an environment where industry, universities, and government collaborate to develop the architecture for the next generation of wireless systems. So we're looking at architectural problems, right? How should the architecture evolve to be able to support all of these new functionalities and programmability and automation? We're looking at developing software stacks. We are working with partners to develop an end-to-end open source software stack that can be used for experimenters and for researchers to innovate in this space in a way that your algorithmic developments don't need to, they can be directly transitioned into real systems once they've been developed in the lab. We're also looking at developing testbeds open for the community, right? Accessible remote testbeds that are fully programmable and enable experimentation and innovation in this space. We are looking also, of course, at a number of algorithmic developments. Primarily, a lot of what we're doing today is looking at control and inference on the radio access network based on techniques from artificial intelligence and machine learning. We're looking at automation techniques. What automation means is automated deployment of functionalities and services on generic compute infrastructure. And we are applying all of these techniques to problems related to security, spectrum sharing, and energy efficiency. Let me try to give you a little bit of a sense of some of the things that we're working on. We're working with a number of industry partners. Some of them are directly sponsoring research. Other partners are just collaborating with us on testing and development of different functionalities. So a little bit on some of the functionalities that you can study and implement with Open RAN, right? Open RAN is an enabler for AI-powered or AI-based cellular systems. What can you do with this openness? The openness of the radio access network enables you, as I mentioned before, to observe the status of the network at different levels of abstractions, at different layers of the protocol stack, and over a distributed network. Take this data, use it to train machine learning models, and also use it to make real-time decisions on the radio access network. So you can classify different things like traffic profiles, mobility patterns, understand anomalies and outages. And you can use these techniques to also forecast, right? Predict what's going to happen to the traffic loads, to the mobility patterns, and to the endover functionalities. And then you can use these forecast abilities to control the radio access network. You can control functionalities like radio access slicing, scheduling, and at lower levels of the protocol stack, things like beamforming, adaptation of modulation and control, and error control, etc. So to give you a little bit more of a sense of the problems that we're working on, what you see here on the right is the open radio access network architecture, where you have the G node B that is disaggregated into the different units that I described before, radio unit, distributed unit, and centralized unit. Then you have two different RAN intelligent controllers, the near real-time RAN intelligent controller and the non-real-time RAN intelligent controller. So the near real-time RAN intelligent controller is looking at functionalities that have time scales of tens of milliseconds to 1 second. The non-real-time break is looking at functionalities with timescales that are over 1 second. Okay, so what you're going to do is you're going to run apps that are third-party control applications on the non-real-time break. The apps can control things like policies, imposing specific models on the network, end-to-end slicing. They have a scale of thousands of devices, and their time scales is over 1 second. So minutes, hours, days. So things like, for example, changing the behavior of the network during daytime versus nighttime, right? There's obviously very different traffic patterns, and you can impose these different functionalities by means of our apps. xApps instead run on the near real-time RIC and interact and create interactions between the near real-time RIC and the G0B. They can control functionalities like load balancing and handover, right? Functionalities that can involve hundreds of devices and have time scales in the order of hundreds of milliseconds. Or they can look at things like minimum access management, slightly lower level functionalities, tens of milliseconds to hundreds of milliseconds, and impose specific scheduling policies or run slicing. Now, one of the contributions of the Open6G project is the notion of dApps. dApps is something that is not yet standardized by the Oran Alliance, but there is a research item that has been studied, and we're hoping that dApps will go into the next generation of the Oran architecture. dApps do two things. They enable interaction with the radio access network functionalities at time scales that are authentic real time, less than tens of milliseconds, doing things like beamforming, controlling modulation, detecting interference, detecting blockage, and things like that. So interacting with things like the digital IQ samples, with functionalities like channel estimation, etc. The other thing that the apps can do is enable interaction with the user plane. So what you see here is just a little bit of a description of what the apps will do, right? And so it's extending Oran into the domain of real time, enabling things like spectrum sharing, beam management and optimization, etc. And also enabling interaction between these third-party control functionalities and the user plane. IQ samples, bits, bytes, and packets, these cannot be transferred to the RAN intelligent controller because of data rate constraints, security, and privacy. So you want applications that run directly on the RAN nodes. And the apps are designed to run directly on the distributed unit or potentially also on the radio unit. We have proposed an architecture for the apps. I'm not going to go into a lot of detail here, but the general idea is, oh, sorry, click the wrong button. The general idea is that there is an agent on the RAN node. It can be the DU, the CU. The agent subscribes to the dApp. The dApp contains the control logic to interact with the agent, and the app can also interact with xApps at the higher hierarchical level that are running on the near real-time RIC. To give a sense of a use case for the apps is spectrum sharing, right? Spectrum sharing on the radio access network. This is an example. This is a spectrogram of a G0B operating around the 3.6 gigahertz. And what you see here is with no coordination, right? If you have an incumbent in the area, and specifically a satellite that could be transmitting at 3.6 gigahertz, well, what you're going to have to do is you're going to have to stop transmitting on the entire channel, right? And that's what systems like CBRS do today. With the apps, you could automatically detect the presence of the interference and block in a seamless way the PRBs, the blocks the resource blocks on the radio access network, and enable the scheduler to continue to use the PRBs that are not affected. This is a little bit of a video that shows AI-driven spectrum sensing done with the apps. What you're going to see is the idea of using real-time spectrum sensing and control, using the radio access network as a sensor, and AI-based spectrum classification on the radio access network. So the system model is what you see here. So you have a ORAN-based G-Node-B. We're going to show in a minute how it's implemented, with a dApp that runs artificial intelligence. Just go back. With a dApp that runs an artificial intelligence model that is trained to identify and classify sources of interference, an incumbent or jammers, or other things like that, automatically block resource blocks that correspond to the interferers, and make sure that the base station can continue to operate seamlessly while avoiding the interference that is being observed. So what you are going to see in a moment is the actual testbed where this is implemented. This is our arena testbed at the Northeastern. That's basically a very large number of software-defined radios with a generic compute infrastructure that instantiates open 5G base stations. Then we're using other software radios as jammers or radars. And this is one of the antennas where the G-Node-B is instantiated, right? So we have antennas that are connected to software radios, and then we have a generic computer system that can instantiate this softwareized 5G base station. What you see here is an experiment. So you have a trained neural network that is looking at the entire spectrum and trying to recognize different sources of interference. Now there is no interference. Now suddenly there is a radar. You see it here at the, on the right, at the top. There is a radar, and this radar is creating interference. The neural network identifies, you see here at the top, the red resource blocks that have been blocked. And the radio access network continues to work seamlessly in spite of the interference from the radar, thanks to the activity of the dApp. And now in a minute, you're going to see that the radar will stop. Okay, so there is no RFI now. The resource blocks are released. And you're going to see also in a minute a jammer, right? There is a jammer now, which occupies a different portion of the spectrum, same central frequency, but less bandwidth. And our module will adjust the PRB blanking to be able to do that. This you can apply some of these techniques to also develop other forms of more sophisticated spectrum sharing. This is some work that we did a couple of years ago that also uses the notion of the apps to classify, to identify the presence of Wi-Fi on unlicensed spectrum bands that are shared between cellular networks and Wi-Fi. So the system is able to use the apps to identify quickly the presence of Wi-Fi and immediately force an handover for the cellular network to avoid the interference with Wi-Fi. So the apps are being, as I mentioned, standardized. We're again hoping that there will be an important component of the 6G architecture, and this is something that has support from a number of different companies, including NVIDIA, Qualcomm, Mavenir, and Dell, that see the apps as an important component into generating the next generation of adaptable, controllable systems for cellular innovation. Obviously, there is a lot of research questions that need to be addressed going forward. What are the use cases and requirements for the apps beyond the xApps and dApps? Architectural differences between control and user plane extensions. How do you mitigate conflicts? How do you create interfaces for the apps? And how do you orchestrate the coexistence between the apps, xApps, and dApps? And time permitting, we're going to talk a little bit about that. Other things that are happening within the Open6G centers. We've been one of the founders of the so-called AI Run Alliance. The AI Run Alliance is an industry university alliance that is trying to promote the convergence between artificial intelligence and mobile networks and radio access networks. It's been spearheaded by a number of companies in this space, NVIDIA has been a major promoter of the AI Run Alliance together with SoftBank, ARM. There's also companies like Samsung, Ericsson, T-Mobile, and others that have been among the founders. We've also been an academic founder for the AI Run Alliance, and it's really looking at three different concepts. First concept is what we call AI for RAN, or AI applied to the radio access network, basically enhancing the radio access network through AI. And this is not in many ways different than a lot of what the academic community has already been doing in terms of AI applied to radio access network to improve the spectral efficiency, optimize functionalities, etc. Right? But it's done with with an approach that is looking at not obviously just developing models, but developing blueprints that can be applied to real systems to enhance the radio access network with AI. The second concept is what is called AI and RAN. Okay, so AI and RAN is the idea of using workloads for RAN. So we talked about the fact that we are virtualizing the radio access network workloads, right? So these are basically compute modules, containers that are run on a generic compute infrastructure, right? Now, once you have a generic compute infrastructure at the edge, right, enabling your radio access network, it makes sense to also run artificial intelligence workloads on this generic compute infrastructure at the edge, right? So you can use the same infrastructure to let AI workloads and RAN workloads coexist and maximize the utilization of assets. And this is something that is very important for operators because operators are seeing their margins shrink consistently over the years, right? And being able to monetize AI on the same infrastructure that will be supporting the RAN is something that is extremely important. But now, obviously, radio access network has very stringent performance demands. So you can't just have a sharing of workloads between AI and RAN without prioritizing correctly the allocation of resources for radio access network workloads. So how do you dynamically orchestrate these workloads is an important topic of research and of activities within the AI Run Alliance. And then there is the last concept is what is called AI on RAN. AI on RAN is looking at AI applications that are enabled or are uniquely, or they can uniquely benefit from the proximity to the radio access network. It's what in a different era we would have probably called edge computing, but it's looking specifically at AI workloads and at the interaction between these AI workloads and the radio access network. And I believe that things like large language models and agents and AI agents, it will make a lot of sense to execute a lot of these things on the radio access network. So in the AI Run Alliance is sort of promoting an evolution from a system where you have a typical architecture with optical fiber connecting a central office to the radio units and with dedicated hardware and signal processing, to an architecture where all of this can happen on a data center that can be powered by different generic compute infrastructure, maybe accelerated through AI. You have a bunch of different resources, right? You have spectrum that is allocated to the area. You have a number of radio units. The radio units can be generic hardware, basically software radios. The software radios are connected with optical fronthaulls, optical switched fronthaulls to the edge data center, right? And then you have compute and accelerators. Now you're going to have what we call an AI RAN operating system. This is something we've been working on in our group quite extensively with something we call zTouch, which is also a university spin-off now. And the AI RAN operating system will take all of these resources and in an automated way deploy a radio access network as well as the RAN intelligent controllers, the applications and all of the services that are needed to provide the service that is needed by the users based on this infrastructure. So in other words, you take all of the different resources that are available, you take an intent, right? Intent can be, I want to minimize latency, reduce the energy consumption, and allocate optimally the spectrum that is available. You give this high-level sort of intent to the operating system. You give the resources to the operating system. The operating system will deploy in an automated way network functionalities that will interface with the radio units to provide the service that is needed. And they will also dynamically orchestrate the workloads to find a desirable balance between run functionalities and AI functionalities, depending on how many resources are available, depending on how much offer traffic exists on the ground, etc. So an important problem, as you can all imagine, is orchestrating the coexistence of AI and run. This is something that we're working on closely and within Open6G. So you have, just to visualize it, right? You have a rack with a computer infrastructure, and you will have different workload types at different servers. Some of them looking at providing radio access network functionalities, and some of them are looking at AI functionalities. And you're gonna have to be able to provide dynamic context switching via intelligent orchestration between these different functionalities. And run functionalities will themselves be divided between communication functionalities and sensing functionalities. And this is a little bit of a depiction of some of the work that we're doing on dynamic workload orchestration. I'm not going to go into too much detail, but there's some work that has been published under the name of Neutron, creating a neutral radio access network orchestrator and scheduler. And there's additional work that's going to be coming out in the next few months. Also, another very important topic that I think is going to have more importance in the next few months is the radio access network as a global distributed training and inference engine, right? Future models, so the first generation of large language models has been based by and large on an abstract representation, right? It's words, letters. These are very abstract concepts. The next generation of models is going to have to be able to reason and control the physical world, right? With automation, robotics, connected drones, etc. We need to be able to create that interface between the logic of language and the logic of physics, right? What is embedded in physics. And for that, we're going to need to have data, right, about the physical world. Where is the data about the physical world going to come from? I think that the radio access network will play a very important role in providing the data that will be needed to train the next generation of foundation models that are going to be able to reason about the physical world. So we're going to be able to deploy sensing tasks on the radio access network, on the generic computer infrastructure at the data center. These are going to be in the form of dApps that tell the radio access network how to observe different data, collect the data, and send the data to data centers in regional cloud, where they can be used to create digital twins of the reality. They can be used themselves to create physical models, and then use these models to basically train agents that will act in the physical world. All right, I wanted to get to a few other things that we're doing within Open6G. I mentioned at the beginning that Open6G is looking at developing open source software stacks. What you see here is basically what we call the software blueprints of Open6G, or its technical architecture. Basically, it has what we call run in a box. That is an open source implementation of the radio access network today of a 5G network, but it's evolving in the direction of 6G. And of course, 6G hasn't been standardized yet. This is based on the open source software stack from the Open Air Interface Software Alliance. We've been working very closely with the Open Air Interface Software Alliance. This is it's basically looking at developing a 3GPP compliant implementation of cellular networks. And they are out of Eurecom in France, but they're a separate entity as of today, and they also opened an entity in the United States, the Open Air Interface Foundation. OAI is then also interfaced with multiple different core networks. We use some commercial core networks, like from a startup here in the Boston area, it's called Day5G. We also use open source core networks from projects like Open5G or Open Air Interface. Then we have created all of the interfaces and data pipelines to connect the radio access network and the core network with near real-time run intelligent controller, non-real-time run intelligent controller. And we've created a set of tools that we call Open Run Gym, right? So Open Run Gym it's been open sourced, and it's a set of tools that enable collecting data at scale based on this open source implementation of a 5G network, using the data to train machine learning models, and then testing the machine learning models in live on a number of different test beds. Specifically, this open source architecture is tested on Colosseum. I'm going to talk about Colosseum in a moment. It's a large-scale emulator that we run at Northeastern. In over-the-air test beds that include Arena and X5G, I'm going to talk about them also in a minute. And then on the test beds in the Platform for Advanced Wireless Research program, or POWER, that Professor Gilbitz mentioned at the beginning of in the introduction. So Open Run Gym is looking basically at enabling experimentation with ORAN and AI in large-scale experimental testbed and networks. So we collect data at scale on digital twins. We design, train, and package the machine learning models as xApps, right? But the idea now is that you can focus on your algorithm. You don't have to worry about all of the plumbing and the software that is necessary to connect xApps with the radio access network that is already taken care of for you. And then you can test your models and your algorithms at scale on different experimental testbed platforms. So let me talk a little bit about our digital twin platform. We refer to it as the Open Run Digital Twin, and it's based on the Colosseum emulator that we have at Northeastern. So Colosseum was originally developed by DARPA to support the Spectrum Collaboration Challenge. And then in 2019, when the Spectrum Collaboration Challenge was ended, Colosseum was moved to Northeastern to join the POWER program, and it was funded by the National Science Foundation with CCRI program that has been supporting it until today. So what is Colosseum? Colosseum is a very large-scale emulator. It has today 27 racks of equipment. This equipment includes generic compute infrastructure, software-defined radios, and FPGAs that are used to emulate channels in real time. So if you look at one, it's organized into different quadrants, okay? So let's take one of the blue boxes here. That's one quadrant. It has 32 standard radio nodes. So standard radio nodes are basically software radios connected with high-performance computing server, right? And then the radios are all interconnected through this massive channel emulator, which is basically a fabric of FPGAs that can be programmed in real time to execute the channels between the different radios. So you have 256 radios in the system. There is 256 times 256 channel relationships. So you have 65,000 channels in the system. And you can basically create models of reality, of specific radio frequency environments, indoor or outdoor, pre-compute the channels or compute them in real time, and have the system emulate the channels that you see in the real world. But now you're doing that with full stack execution, so you can instantiate the G-Node-B with 3GPP compliant software, and all of the machinery of things that we discussed earlier, including near real-time rake, no real-time rake, etc. The system is remotely accessible, so there is a whole management infrastructure with experimental websites through which you can define a specific experiment that you want to obtain, and it has a large number of GPU nodes, NVIDIA A100 and V100 and others, that can be used to train your models or for inference in real time. So to give you an idea of things that you can do with Colosseum is you take a model of reality. This is the area of Rome, Italy, where the real Colosseum is, but you can take any outdoor environment. Like you look at the location of base stations in that environment, and then you can use a RF propagation modeling tool to calculate the channel between different mobile nodes and the G-Node-Bs, and you input that into the massive channel emulator. Then you're going to map different software radios to different G-Node-Bs that are executed with the Open6G technical architecture, right? The Open6G blueprint. So you can create the different base stations, and also you can create in software the different UEs or programmable nodes. So in this example here, you have 7 different base stations that are instantiated in that area with 42 different users connecting to the different base station. And now you can also connect all the machinery that we discussed before, near real-time rake, no real-time rake, train your machine learning models, etc. And run these experiments, which are very high fidelity and very, representing a network full stack with real applications, with mobility, and all of the characteristics that are in a real network. And this is obviously something that, even for companies in the field, it's a capability that is very valuable. So we collaborate with a number of companies in developing algorithms. Some companies prefer to use this on their own to develop their own things. Some other companies collaborate with us, but it's certainly a valuable tool that has been evolving quite significantly over the last few years. And to give a sense, we have a tool chain that we've developed internally through which we can take a real-world environment. This is an area of Tampa, Florida, and you can use this toolbox to develop representations of this environment that can be run in Colosseum, and the same we can do for indoor environment. We create a 3D representation of the environment, and then we use ray propagation tools to create the channel impulse responses that can be enabled in Colosseum. So this is an example of things that you can do. This is GUI. You have a specific G-Node-B. It's all softwareized, implemented with our software architecture. This is in Barcelona, Plaza de Catalunya, and you have different users. You can move them with your interface, right? And the channels in Colosseum are evolving in real time. They're being updated in real time to represent what you do on the graphical user interface, so the position of the nodes and the propagation environment in Plaza de Catalunya. But what you get is, it's not just a ray tracing propagation. You get the application level performance because you have real applications in a real protocol stack that is running on the system with all of the functionalities. So if you want to test a new scheduler, for example, you can do that as part of this framework. Another testbed that we have been developing at Northeastern is something that we call X5G. Okay, so X5G is an ORAN and 5G compliant research infrastructure. It's been developed in collaboration with NVIDIA and the Open Air Interface Software Alliance. It's the first open and programmable network that is fully accelerated on GPU, and that is completely multi-vendor and following the Oran architecture, and also in an automation environment. So the general idea is as follows. There's 8 nodes. Of these 8 nodes, they're in 2 different buildings at Northeastern, in fact, with geographical separation. So it's in 2 different campuses in the Boston area. 6 of these base stations are on one campus, and 2 are being deployed outdoor on the second campus. The architecture is as follows. So we have commercial radio units developed by Foxconn, but we also have other developers for this. The commercial radio units are interconnected with an Oran 7.2 interface with the baseband processing that is running on NVIDIA GPUs based on the ARC framework that is completely accelerated on GPUs. So this is a piece of hardware. This is running on a server accelerated with GPUs and implements the baseband processing of Hi-Fi. The layer 2 and layer 3 of the protocol stacks are connected with with a FAPI interface and are implemented with the OpenAir interface software stack. Core network is based on Open6G, and then this whole thing that is implemented in, as I said, on generic compute infrastructure is integrated in an OpenShift environment. So OpenShift is a Kubernetes, it's a Red Hat version of Kubernetes. It's basically a microservices orchestrator. So what we can do with OpenShift is to instantiate at the click of a button this entire network with 8 base stations, all in software on this generic compute infrastructure, right? And this is a live network that researchers and students at Northeastern can use. It provides today up to 1.4 gigabit per second of downlink throughput, and it's being used as a semi-production network. It also has all the things like near real-time rig applications running on that, etc. So this is a little bit of a video showing some of this work and how this has been implemented. Multi-vendor, softwareized and order compliant. These are the various different architecture I described. And this is in the lab environment showing real phones that are connecting to the network. This is in our previous building. We've since moved, so the architecture looks a little different now. But we have the ability to, there's different phones that you see here at the bottom right that are running different applications with different characteristics. This is the control center that visualizes all of that. And what you see on the left is the network running on the generic compute infrastructure. Okay, I'm going to conclude with a couple of different, just a couple of different things that I wanted to mention. Now, automation and building continuous integration and continuous deployment pipelines is something that I think is going to fundamentally change how we do research on wireless in the next few years. This is just showing a little bit of the platforms that I described, right? Colosseum, showing the platforms that I described, Colosseum here on the left, X5G here, and some of the other testing platforms that we have. And so in the past, right, if you were to develop a new functionality, what you would do is you would test your new functionality in MATLAB or into a network simulator, etc., right? But you would test your new functionality somewhat of in isolation with respect to the rest of the system. Today, with this availability of CI/CD, CD pipelines, if I develop a new scheduler, for example, right, I can implement my new scheduler as part of the OpenAir interface software stack, we can build with this automation framework a container image that will include the new scheduler with the latest release of OpenAir interface software stack. Then I can automatically test my scheduler in emulated run on Colosseum, right? Then I can take the same container, implement it over the air for automated testing over the air, for example, with the X5G software stack that I described before. Then you can analyze the results automatically as the test passed or as the test failed. So what you've developed works or it doesn't work. What's the performance of the algorithm that you've developed? And what is the power consumption resulting from your experiment? And this can all be done today in a pretty automated way. I mentioned earlier a lot of the work that we're doing in automation and testing. We have a spin-off of the university that is called zTouch Networks, and it's doing what we call intent-driven automation. So it's looking at taking high-level intents, right? I want to, for example, support ultra-low latency UAV traffic and 4K video streaming for asset tracking. We have an intent processor that converts this high-level intent into machine understandable intents, and an orchestrator that takes the AI models from a service, from an AI and service catalog, and deploys them and implements them in the form of xApps, dApps, or rApps, or specific services to be able to provide the service with the characteristics that you have defined at a high level. And you can also train models based on data available in a data lake to be able to provide the service that you need if the model is not available already. Okay, so we think that this ability to orchestrate and automatically deploy systems with control that is optimized for a specific service is going to fundamentally change how networks are deployed, and it's going to be a very important part of what we call 6G. And with this, I'm going to pause and stop here. I could go on for another hour, but I don't. I think we have enough for a good Q&A session. Thank you.
Thanks a lot, Tommaso. Excellent presentation. We learned a lot. There are many questions, and I will start to read them to you. And there are also a couple of them that one of them, the verb is missing, so I couldn't figure out what the person was asking. There were two other questions that they were anonymous. I don't know why anonymous. So I asked him or her to ID themselves. So the first question is from Timothy is. He's the student of Lichun Wang. He's one of our Georgia Tech alumni. As you know, he graduated before you, like 1995 in Taiwan. So he's asking, apparently he met you in Summit 2024. He's asking that NVIDIA solutions, or he says or solutions have come out and they provided API for their AI interference. I would like to ask, what's the possible technical challenges of developing E3? Say if I want to deploy my SLMs on dApps.
Okay. Thank you, Tim, for the question. Oh, in inference, so it's commenting there is inference, not interference. So if I understand the question, you're asking if the E3 interface, which is what we have developed and proposed for the apps interacting directly with run nodes, so interacting with the CU and DU, can be used to connect, to basically provide an interface for SLMs and LLMs interacting with the radio access network directly. Is that, do I understand the question right?
You can type again. So in the meantime,
yes,
probably.
Also, yes. It's thing.
Are
yes.
There
so
any yeah, go ahead.
Yeah, I think that's an option. Another option would be to have the to intermediate the interaction between the large language models with xApps or rApps running on the RIC. I think that would make a lot of sense. And then having the large language, the xApps communicate with the dApps that would implement in real-time control. The problem is sometimes, when you run logic on the apps, you need authentic real-time control, closing the loop in real time. So you're observing something and you need to take an action within microseconds or a few milliseconds. If you are trying to make that decisions on agents that are farther away from the radio access network, you might not be able to close the loop fast enough. So with logic that is directly on the apps, could be itself maybe controlled and configured by hierarchically higher level large language models, you can guarantee the performance. And we've open sourced the apps together with experimental data that shows that you can in many different situations run the apps with latencies of a few hundreds of microseconds on generic compute infrastructure. So that's probably what you need to be able to interact with hierarchically higher level large language models. Thank you for your question.
There's another question but from Umral. He says, are there any virtual to physical links implemented for network modification, network management in the presented digital twin architecture?
Yes, so I didn't talk about this. It's a great question. We have a paper that was published at GlobeCom last year, GlobeCom 2024, that looks specifically into this. It's called the TwiNet, and it's basically developing an architecture to link the physical world links in basically a radio access network, a testbed, to the Colosseum emulator, so you can reproduce in real time the characteristics of the real world network into Colosseum. Great question, thanks.
There are many other questions. So another one is from Brock. He says, compared to legacy solutions, softwareized, virtualized solutions demand more computing power on the edge and or center. How to balance this power and energy requirement? And he also says that thanks for the fantastic presentation.
Thanks for the question. This is indeed a very important problem, right? And it's obviously, if you have something that is very carefully and in a detailed way implemented for a specific hardware, you lose flexibility, you might gain in terms of efficiency, right? But losing flexibility also comes at a price, right? Because losing flexibility means that you're not going to be able to adapt the behavior of your network to the specific environment where you're operating, right? That means also sometimes using energy. So there is a balancing act here. I would say that nobody has all the answers. One of the projects that we have from the NTIA Public Wireless Supply Chain Innovation Fund, we started about a year ago, is trying to provide answers to this question. So we are developing a measuring infrastructure that is trying to measure the energy efficiency of the radio access network, including of the open radio access network, right? Including all the components. So we want to measure the energy consumption of the radio, of the computers, of the servers that are running the radio access network, of the AI that controls the network. So end-to-end of the core, right? End-to-end, everything that you need to run those services and compare to a legacy network. Also be able to dissect, right? How much of my energy consumption is coming from core? How much is coming from AI? How much is coming from specific functionalities? And then, once I am able to dissect and understand what components are coming from where, can I optimize those components, right? So open problem, open questions, efficiency of energy efficiency of open radio access network, and a lot can be done there.
Thank you, Tommaso. There are so many questions. It's unbelievable. So this is the most active Q&A session we had a long time now. So Edwin is asking, how likely do you think it is that dApps become widely accepted when some of the major telecom vendors have already declined, considering the non-RT RAC and xApps?
This is also a great question. I can tell you that there's there's vendors that support dApps and don't support xApps, which may sound counterintuitive, but they're saying that xApps are basically already part of what they do with their SON infrastructure and things like that, while dApps can provide new functionalities that don't exist today. I don't have the answer, right? But what I can tell you is that there's a lot of vendors that have been supporting the notion of the apps. And everybody has their own internal convictions and politics, right? There's some vendors that they like xApps and they don't like our apps. Some other vendors, they like our apps. And at the end, it's going to be a balancing act. We'll see in a few years, but I'm confident that there is there's, as I mentioned before, companies like NVIDIA and Qualcomm, they're very much supportive of the apps as it looks today.
And another question again from Umaral: how can we manage the complexity of multi-user intent networks in the presence of conflicting AI-based optimization actions?
Very, also very pertinent and great question. I'm not going to attempt to give you a complete answer because that's but there is a, just wanted to say that there is a portion of my presentation that I didn't go through for lack of time when we would have talked about conflict. And the idea is what you're seeing now in this slide here, right? Where you have multiple xApps that are providing potentially conflicting actions to the radio access network, right? And the problem is that you're going to have multiple dApps, xApps, and apps coming from multiple vendors. There could be multiple intents that are requesting conflicting actions, right? And so how do you first understand what xApps are going to create conflicts? And second, how do you mitigate these conflicts that could come from different acts? So we have some preliminary answers to this question. We have a paper that is published in Archive. It's called Pacifista or pacifier, right? It's the Italian for pacifier. It tries to develop statistical techniques to understand the conflicts, which xApps would create conflicts, and then how can you mitigate the conflict between these different xApps. It's on Archive, again, Pacifista, and you can take a look at the paper. It's on my website if you're interested.
Thank you, Tommaso. I hope Alessia is not getting impatient now.
No, it's okay.
Too
Yeah,
many other
thanks.
questions.
Please go ahead.
They're really interesting questions. And so there is another one. It shows that we are worldwide here. Deng from Aalto University in Finland. He is asking, I will shorten it. So there is a potential for converging RAN and core functionalities to optimize latency, in particular for URLLC applications and enhance user experience. In this context, how can AI-driven automation network intelligence enable and support such convergence?
Oh, this is a great question. It's basically asking how AI RAN can meet AI core, right, so to speak, or how you can have a end-to-end control and orchestration of the functionalities that includes basically control on a fine-grained access on the radio access network with optimizing the functionality at the core to prioritize specific traffic. That is something on which I have not seen specific work addressing this problem, but it makes a lot of sense to do that, and I think that would be an excellent research topic to be looking at.
Thank you. And there is also from one of our alumni, Janice from University of Florida, is asking, excellent talk. Do you foresee any new cybersecurity attack surfaces that may develop in this new environment?
Yes, absolutely. Hi, Janice. It's great to not see you, but see your name and your question. let me see if I can you see my slide now? So this is, I mean, I think a high-level slide that basically answers your question, right? Are there new attack surfaces that are enabled by the the Open Radio Access Network and the new interface? I think the answer is, broadly speaking, yes. At the same time, obviously, there's a lot of new opportunities that come with a new architecture, with intelligence that comes with it, right? So there's new interfaces, these new interfaces between the different components, they need to be secured. So challenge number one is, how do you secure these new interfaces? You need to make sure that you don't have an agent spoofing a specific CU, for example, or a specific DU, right? You need to be able to authenticate the different components and make sure that whomever says I'm the legitimate DU will actually be the legitimate DU. And so we've done some work at Northeastern in collaboration with Kaushik on securing the open interfaces, specifically on evaluating the performance of encryption on these open interfaces. Like, how much is the overhead that you introduce computationally with encryption? What is the overhead in terms of energy consumption and performance penalty that you pay through encryption? The other part is securing the infrastructure, right? You're now running this open programmable radio access network on a virtualized infrastructure. There can be multiple vendors in this shared environment, and you could have multi-site deployments with different edge and cell sites. So this infrastructure needs to be secured. The great news is that you can use CI/CD and automation. These techniques also come with a lot of best practices from the cloud world in terms of security, but from the perspective of the wireless vendor, this is something new to be considered. And then the third component, which is very interesting from a research perspective, is securing the intelligence, right? So you're going to have now machine learning agents providing different time scales, as we saw, in different parts of the network, intelligent control actions. And how do you make sure that they're doing what they're supposed to do, that the data that they're trained on has not been poisoned, right? That are not backdoor and back channel attacks. And so all these things need to be studied. I think I've been seeing more papers on this area in the past year, but it's still a pretty underexplored area.
There are a couple more questions, but I would like to ask my questions, and then I will come back to the last two because they are trying to ask for international collaborations. They're important questions, in my opinion. So my question is, your title has this integration of orchestration, conflict management, and explainability. So the question is, can a unified framework address all three aspects simultaneously? Somehow I missed that.
Yeah, that's a great question. I don't think that we have a unified framework today. We have done quite a bit in terms of orchestration. We've done some in terms of conflict management and explainability. But there needs to be much more work to come up with a completely integrated framework that addresses all three. So what I would say is that in terms of orchestration, at this point, we have pretty mature solutions. In terms of conflict management and explainability, we're at the beginning of the journey in many ways.
And another short question is about benchmarking and data sets. Is there a lack of standardized data sets for evaluating AI in next generation networks or the next scenarios?
I would say absolutely yes. So I would say that there are data sets, but they're far from being standardized, right? There's a lot of different
or used commonly. Is there a data set or that people can use freely?
So, for example, we have we have released a data set that has been collected, that's been generated with Colosseum, that is used for, it has a lot of data that is related to providing a lot of metrics and performance related to cellular virtualized networks. It can be used for problems like scheduling and slicing with AI. A lot of people have been using it, but I would not say that it's a standard for that. I know that there are efforts by a number of different entities, including NIST, to try and create a standardized data sets for this, and that's a very important effort. Where there's still a lot of everybody's doing their own thing kind of approach, and it would be good to be able to compare the results with the same data sets like the computer vision community has been doing.
And thank you. This is a very good answer. So Tim is asking, actually, I can answer, but you can also give your opinion. He's asking for international collaborations between NSF and Taiwan NSF. Are there any joint proposal opportunities? To my knowledge, there is this international program within NSF that you can apply with a partner from the US, with any country, by the way, not only Taiwan. And so it exists, Tim. And then he is asking also for control cloud access to Colosseum like testbeds. Maybe you answer that one, Tommaso.
Yeah, so for let me start from the Colosseum access. It's in general, we try to provide remote access to partners and people that are willing to use that. Researchers from nonprofit, we usually provide access unless we're prevented by law from doing that. So absolutely reach out to me if you'd like to use Colosseum. In terms of international collaborations, I mean, we're very open. It's usually the problem is these things are complicated. They're underfunded, these international collaborations, and it's also complicated. You need to get the proposal approved on both countries, and so the probability of success is the joint probability of success of the two things. So if you have 5% on one side and 5% on the other side, you can do the math. They're often very hard to get.
And there is also a question from Destin. He is the leader of the Kakuma Hub Africa with AI for Good. And he wants to ask you how you can expand these activities to the remote areas, meaning how can you involve Africa in these activities? It's actually a good question.
It's a great question, and I think to give you a good answer, I would probably need to learn a little more about what you're trying to do in AI for Good. But I would say that we're very open to try and see if there's ways that we can expand the impact and collaborations with different areas of the world. So if you have any specific ideas, I would absolutely encourage you to reach out, and we can talk about potential collaborations in this space.
Maybe also use the international program of NSF, right? And writing some joint proposals and try to involve the African countries also in US activities. There are more questions.
Absolutely. There is a lot of interest
also, but I think we should finish it here. I thank all the audience and also the folks who asked questions. I would like to apologize to those that we could not cover their questions. And please feel free to contact Tommaso Melodia and ask your questions directly. He's very approachable. I'm sure he will get back to you and answer your questions. And I again thank you, Tommaso, for this excellent talk and also the Q&A session. So Alessia is taking over and will ask you some life lesson questions. And again, thanks a lot.
Thank you so much, Ian, for moderating this very interesting Q&A. As you said, probably the richest we ever had. So it means that the speaker was great and the subject is very interesting. So thank you, Professor Melodia. So now we move to the Wisdom Corner. So I will ask you a few questions. This is a special corner offering a unique special angle to the series of webinars to add a personal touch. So looking back on your journey, what is the most valuable life lessons or even a failure you have encountered that shape your path? And how can this lesson inspire or guide those attending the webinar today?
Sure. Well, what I would say is that you know, a lot of researchers, and I think I was no exception, right? Start their research journey by thinking that they're pretty smart, right? It's very common, right? You have people that have been studying, science, technical subjects, engineering, and if you're getting into a PhD program and you're studying a research career, in general, most people they would tend to feel pretty good about themselves, right? And their capabilities. And then, when you start a research, and Professor Hildes knows this very well, having been, with me in the early stages of my career, you start figuring out that it's not easy. It's not easy at all, right? And even if you've been maybe able to, crack math exams and and do very well at them. Starting a research career and research journey, it's a whole different ball game, right? In which there's a number of different how can I say skills that come into play, right? And one of them is certainly resilience and persistence, right? Things are not gonna go exactly the way you had anticipated from day one and from the beginning. You're going to, you're going to fail at getting your conference paper accepted in your dream conferences. You're probably not gonna get your dream job when you start your career. You're gonna have to do things that are quite different from what you had anticipated when where you were picturing your ideal research career at the beginning. But I've been now. Of course, I've been at this for a while, right? It's been almost 20-year career since I started. I mean, it's over 20 years since I started my PhD, and I can tell you that absolutely, persistence and being, continuing to pursue what you think is right, the way you think is right, is the most important thing for pursuing a successful career in this field. And this is something that, and it's something that, when we were a student with Professor Hildes, he would mention all the time. And I also tell that to my students and to a lot of the younger researchers that I mentor. But you don't really see that unless you experience that on your own career. I mean, you can understand that in abstract terms, but it's a different thing to go through the experience of seeing that with your own eyes.
Yeah, no, very clear. Well, you anticipated my next question on which skills and qualities the students should focus on to have some success in their career, in academic, in research. But I would like to ask you what first inspired your passion in your field, and how did you turn this interest into an important and meaningful career?
Oh, man. So, the interest came from, I've been fascinated with computers since I was a child. So that was something that I was absolutely. So I started coding in BASIC when I think I was 7 or 8 years old, and that was it was absolutely magic to me. Then, actually, when I was a teenager, I did a lot of different things. I wasn't spending a lot of time on computers at that time. But then I still had that very, very clear in my mind that I was, and then, the first time that I was able to send an email in the very early days of the internet to a friend that I've moved I grew up in Rome, Italy, and I had this friend, very close friend, who had moved to Brussels in Belgium, and we were able to exchange emails, and that was absolutely magical to me. And so that's how I decided that I wanted to study telecom and pursue a career in that. And then during my PhD years, it's been super exciting in terms of understanding how to innovate, right, and look at completely new problems that nobody had looked at before, and not only understanding, but and being able to model and design, but being able to think about the future, right, see the future and innovate, and that's yeah.
Very clear. Is there any emerging trends or groundbreaking topics that you would advise today students to study, to explore? The young researchers.
Look, I think it's it was obviously my area of expertise is in telecom in general. I think it's a great time to be in wireless and telecommunications in general. It's not, if you look at media hype, it's probably not the hottest topic today. But if you look at the various trends and technologies and the convergence, which is, it's a lot of what I do, right? The convergence between wireless computing and intelligence. It's an extremely interesting topic, and I think it's in many ways much more interesting than some of the applications of artificial intelligence to different topics, right? To other areas, because of this, tight connection between systems, intelligence, and communications. That's what I really enjoy doing, and I think that there's wireless systems are going to change significantly in the next 5 to 10 years. And there's a lot of exciting work that can be done.
Wonderful. My last question, among your career achievements, is there one particular contribution, whether professional or personal, that has a profound impact on you or on others? And what makes this accomplishment especially meaningful to you?
I have to say that, in the earlier days of my career, I've been working a lot on communication systems in extreme environments. I've been working in underwater communication and networks. That's something that is still very close to my heart. We started at Georgia Tech with Professor Gilditz and still working on that quite extensively today. And I think that there's been a lot of progress in that space, and that's something so unique and impactful that I think that's very important. Also, we've been working over the years, and that's been a little later in my career, on communications inside the human body, with unconventional physics and communication techniques, and that is something that also it's quite impactful and different, and again, it holds a special place in my heart and and in my career journey.
Wonderful. Thank you so much. Ian, would you like to come back with us? We conclude this webinar. Very interesting webinar. Thank you so much.
Thank you again,
Thank you,
Tommaso.
Alessia.
Thanks a lot, Alessia. It was indeed a fantastic day. It's April 1st, but it was a good day, right? So, really, thanks a lot, Tommaso. So we continue our webinar in 2 weeks, right?
Yeah, on 15th of April with
Yeah, with
Dr. Elsa Erkip
that's right.
from New York University.
Information theory-based talk, very good speaker too. And I'll be in Abu Dhabi, so next week I'm flying there, so there will be no time difference, almost no time difference. So thanks a lot again.
Thank you very much, Professor Melodia.
Yes.
Thank you. Thank you.
And
Bye-bye.
Thank you. Thank you for having me. It's been a pleasure. Thank you.
Thank you.
Thanks
all.
a lot.
Ciao, ciao.
Bye. Bye-bye.